Hello?
Hello, sir.
Yeah, hi. Let's just wait for Rishi to join in.
Yeah,
Okay. So we'll try to do chapter number 6 today.
yeah,
Okay. Uh, so this is about carbonyl group. Carbonyl group has C double bond O and some things are connected here. And we are going to talk about nucleophilic attack on this, right?
Yeah.
Nucleophilic addition.
yeah,
So we have understood in the previous chapter what nucleophiles are. Nucleophiles are basically electron rich species.
Yeah.
yeah,
Domain.
Yeah, and they are looking for a carbon which is positive, which has a tiny positive charge, which is exactly what is the case here.
Yeah.
mm-hmm.
So any electron rich species which has a lone pair of electrons to donate, or an empty orbital, or a filled orbital,
Single
right,
orbital. Yeah.
which can share with someone else, so that will try to attack this carbon, right?
Yeah.
Yeah,
So generally the reaction has two steps. There is nucleophilic attack on the carbonyl group, and when that happens, since it has donated a pair of electrons to an unfilled orbital here, right?
Mm.
mm,
Yeah.
So the unfilled orbital here we discussed in the last class is the pi star.
Five star.
That is the lowest unoccupied molecular orbital, right?
Yeah.
yeah,
Because all the orbitals, actually 4 bonds are formed for the carbon here, right? It's
Yeah.
not like this carbon is deficient in electrons. It's just that two of the electrons are in pi bonds, right? That
Yeah.
are slightly
yeah,
high energy.
Mm-hmm.
When they are in
Yeah.
pi bonds, there is a pi star which is unoccupied, right?
Yeah. Mm.
So that pi star will be filled by the 2 electrons that come from the nucleophile. And as soon as that pi star is filled, there is a sigma bond that forms with the nucleophile, and the pi bond therefore breaks.
Yeah.
yeah, yeah,
Pi bond breaks, and this comes on this, and you get an anion. So you get
Yeah.
something here, the nucleophile attaches, and you
Oh
get an
minus.
anion here,
Yeah.
right?
mm,
This is the first step. The first step is the addition step. And the second step is protonation of the anion. So maybe it is in some solvent, like if it is in
Acetic.
water.
H2,
Yeah.
yeah,
So if there is H plus available somehow, or then it will be protonated, right?
Yeah.
mm,
This will form a bond, and eventually you will get a C nucleophile and an OH here, right?
yeah,
Yeah.
So
Yeah.
that will be the product, right? Correct.
Yeah.
mm,
So now what we will go to is the first section here. He's just talking about molecular orbitals which explain the reactivity of the carbonyl group, right?
Mm-hmm.
So the first reaction he talks about is the NaCN. NaCN H2SO4 is being added to the carbonyl group, right?
Yeah. Yeah.
NaCN H2SO4 means basically there is a cyanide ion that is present, right? Cn
yeah, yeah,
minus is present, and in the cyanide ion we know that the electrons that will be donated will be on carbon, right?
Yeah.
So the nucleophilic portion is the carbon electrons, right?
yeah,
These two will be donated because nitrogen will hold its electrons very strongly.
Yeah. Yeah.
Nitrogen also has a lone pair, but it will not be reactive, right?
Yeah.
mm,
Okay, so here the first step that happens is basically the same thing that we just now discussed. Cn minus attaches, right?
Yeah.
So you get a Cn attachment and O
O
minus
minus, yeah,
happens. And because H2SO4 is there in the solution, there is H plus completely available, and
mm,
that becomes your cyanohydrin is formed.
Yeah. Yeah.
This type of compound is called a cyanohydrin, right?
yeah, yeah,
I think that is what it is called. Let's just see what he's calling it. Okay, fine. Then in the next page, he's talking about why does cyanide in common with many other nucleophile attack the carbonyl group, and why does it attack the carbon atom of the carbonyl group, right?
Yeah.
To answer
That's
these questions, he will talk about the polarity, right?
yeah. Positive
So,
charge.
so the carbonyl double bond, like that found in alkenes, consists of two parts: one sigma bond, one pi bond. the sigma bond is between the two sp2 hybridized atoms. So here the oxygen is also sp2 hybridized because there are some lone pairs here.
Yeah, yeah.
And he talks about sigma bond, pi bond. We have already discussed all this, right? So basically there is a pi bond that is there, and the pi star is the anti-bonding orbital, which is empty, right?
Yeah.
We have already discussed here. So if you go to the bottom of the page, he talks about, because there are two types of bonding between C and O in the carbonyl group. He's talking about the carbonyl group here. There are two types of bonding. One is a sigma bond, and this is a pi bond. Therefore, the C double bond O is rather short than the typical CO single bond, right? And also over twice as strong. So, right. So why is it so reactive? Why is it so reactive still? Because of polarization. The polarized CO bond gives the carbon atom some degree of positive charge, and this charge attracts negatively charged nucleophiles like cyanide and encourages reaction, right? So again, now he's describing the same thing in much more detail. He's drawing the orbitals also. Okay. So in the next figure that you see, you will see an anti-bonding orbital is on carbon. The brown one is the anti-bonding pi star. Okay. That is more on the carbon, right?
Yeah.
Because it is slightly positive charge there, right? So electrons are spending more time towards the oxygen, right?
Yeah.
So more portion of the anti-bonding orbital will be on carbon, and more portion of the bonding molecular orbital will be on oxygen.
Oxygen. Yeah.
Right. So that is what he's saying. And at below that diagram, he talks about, notice how the trigonal planar sp2 hybridized carbon atom of the carbonyl group changes to a tetrahedral sp3 hybridized state in the product. So if you look at this carbon atom here, it is sp3 clearly, right?
Yeah.
And the structure will become tetrahedral, right? So basically the structure has changed from a sp2 trigonal planar structure to a tetrahedral structure, right?
Yeah.
That is the change that happens as a result of this reaction. Okay. The next section is attack of cyanide. He's just talking about cyanide, particular reaction of cyanide. So cyanide contains sp hybridized C and N atoms, and its HOMO is an sp orbital on carbon. So, so what is the highest occupied molecular orbital here? The pi orbital.
Yeah.
This is an sp hybridized carbon because there are two lone pairs, one here and one this. Two charge clouds, right?
Yeah.
So there are empty p orbitals also available, right? Empty p orbital is there, actually filled with a lone pair, right? Correct. So if you look at the bond here, there will be two p orbitals that will be left over, right?
Yeah.
So actually both the p orbitals are no. So one sigma bond is formed with the sp, and two p orbitals will form pi bonds, and one p orbital will carry the lone electron, lone pair, right? Okay, so makes sense. So the sigma, the pi orbitals which form the sigma pi bond, right? The p orbitals which form the pi bond, those are the ones that are, I think, available, right? Pi star, right? Pi star for that will be available. Correct?
Yeah.
Okay, so he's talking about the highest occupied molecular orbital of the Cn minus. So basically you have to compare. Okay, so you have to compare the energy levels of the pi star and the sigma star, right? Sigma star of the sp orbital, right? And pi star from the p orbital. So he is saying here that the sigma star is higher in energy, which makes sense actually, right? Why does it make sense? Because sigma will be a stronger bond, so it will be lower in energy. And pi bonds will be here somewhere, right? So pi star will be here, pi star, and sigma star will be here, right? So the highest occupied molecular orbital. But why is it occupied? It will not be occupied. Okay. That is the issue, right? HOMO. Why will it be a HOMO? Is the CN molecular orbital diagram drawn in the previous chapter somewhere? CN minus. Maybe it is somewhere. When he was doing in chapter number 4, I go back 1 second. Because we should know which one is occupied and all. So CN minus, just see if there is a CN minus diagram somewhere. Hybridization, carbonyl group. Okay. Right now I cannot find CN minus, right?
Yeah, I can't find it.
It's fine. Right now he is saying that the HOMO is the sp orbital on carbon containing lone pair. HOMO is the sp orbital on carbon containing lone pair. So what is he saying here? He's saying there are two sp orbitals will come, right? Two sp orbitals should be formed, right?
Yeah.
One of them forms a sigma bond.
Yeah.
One of them, he's saying, will be empty. Huh? Oh, yeah, makes sense. No, one of them will carry the lone pair. No, one will carry.
Yeah,
one will carry lone pair. One sp. Okay, the second sp is involved in sigma bond, right?
Yeah.
And the two p orbitals that are left over are involved in pi bonds.
Pi bonds, yeah.
Right?
Yeah.
So now the comparison of energy will be between occupied orbitals. Let's talk about occupied orbitals, right? So occupied orbitals will be there in the sigma bond and in the pi bonds, right?
Pi bond, yeah.
So now these two you have to compare with the lone pair, right? Okay, makes sense, right? sp orbital with the lone pair is not being lowered by bonding, right?
Yeah.
There's a filled sp orbital with the lone pair, right?
Yeah.
Definitely it will be higher energy than this,
Higher,
because
yeah.
this is the molecules orbitals, right? Because the bonding electrons are lowered slightly, right?
Yeah.
So now it makes sense, right, for everyone.
Yeah.
So there is a filled sp orbital which is carrying the lone pair, which is the HOMO, right?
Yeah.
Everyone is agreeing on that, right?
Yeah.
Okay. So that is going to react with the sp orbital. That is going to react with the pi star orbital of C double bond O.
Yeah.
Right? Pi star orbital of C double bond O. Right? That is the lowest unoccupied molecular orbital here. Right?
Yeah.
Correct.
Yeah.
The reaction is usually carried out in the presence of acid, which protonates the resulting alkoxide, right, to give the hydroxyl group of the composite functional group known as a cyanohydrin. So finally a cyanohydrin is formed and you get a OHCN type of situation after protonation. Right?
Yeah.
The reaction works with both ketones and aldehydes. So what is the difference between a ketone and an aldehyde? A ketone is this, where there is a carbon here. Carbon, okay. And a aldehyde is this. There is a hydrogen. Okay.
Yeah.
So this is a ketone and this is an aldehyde. Okay.
Yeah.
So obviously this doesn't influence the reaction so much. It is still electrophilic carbon, and you still get this nucleophilic attack, right? So on both of them it works. Okay.
Yeah.
Then okay. So he is giving examples of both of them. So cyanohydrins in synthesis, that box, right? Cyanohydrins are important synthetic intermediates. For example, the cyanohydrin formed from this cyclic amino ketone. So for example, look at this. This cyclic compound is there, and on the hexagon there is a double bond O, right?
Yeah.
So there is a ketone, right?
Ketone, yeah.
So when you do NaCN and H2O, it will become OHCN there, right? And that is coming with 95% yield. And later, if you add other reagents, you will get some medicinal compounds like 5-HT3 agonists, which are designed to reduce nausea in chemotherapy patients. Okay, so this is intermediate. This is an important intermediate in many useful compounds. Okay,
Yeah.
so many natural and industrial products such as insecticides and all are formed using this. Okay.
Yeah.
Okay, then we come to cyanohydration. Cyanohydrin formation is reversible. Okay, so like mostly all reactions, this is also an equilibrium. Okay, so
Yeah.
so the formation of cyanohydrin was happening when you took a ketone and you added some Cn minus in a acidic solution, right?
Yeah.
And then you ended up getting R OH Cn.
CN.
Yeah.
Right? But this is a reversible reaction. How do you get this back? Right? You put it in some basic situation.
Basics. Yeah.
NaOH H2O. Right? Now what happens here? He is describing here. What happens is the OH minus from NaOH, right?
Yeah.
OH minus from NaOH will attack this H.
Yeah.
Right? So because it attacks this H and it takes away this H, you get back the O minus situation, right?
Yeah, yeah.
You get back the O minus like this, right?
Yeah.
And then it is likely that this can leave, right?
Yeah.
This leaves, the Cn minus will leave and O, this minus will form and you'll get the reverse step, right? You'll get this and plus Cn minus, right?
Yeah.
This electron pair will go to the cyanide and this minus sign will come here. Once the H has been taken away by OH minus, right?
Yeah.
Correct.
Yeah.
So he's talking about here, there's one sentence that he writes, this is because cyanide is a good leaving group. So it can leave easily. And we'll come back to this type of reaction in more detail in chapter 10. So this leaving group stuff, not everything will leave very easily like this. Okay.
Yeah.
It will break the bond and go out and it is fairly stable. Right?
Yeah.
So cyanide is a good leaving group. That is why this is happening. And we'll come back to that later. Right? Right now, we don't want to worry too much about it. We just know that if you dissolve the cyanohydrin in water, right? Dissolve in water. Even then, even if you don't have this, you still get some amount of reversible stuff happening.
Yeah.
Even water can act like a base, right? A little bit.
Yeah.
Not a lot, but yeah. And if you have a strong base there, then obviously to a high degree, you will get this.
Yeah.
Right? Okay. So he's saying cyanohydrin formation is therefore an equilibrium between the starting materials and the products. And we can get good yields only if the equilibrium favors the products, right?
Yeah, yeah.
The equilibrium is more favorable for aldehyde cyanohydrins than for ketone cyanohydrins. So he's saying that this cyanohydrin, right?
Yeah.
Is not so favorable,
Less favorable
as compared to this cyanohydrin. Okay. So aldehyde, if you take an aldehyde and add NaCnH2SO4, that gives a higher yield of the product. That favors the product more as compared to a ketone. And why is that? Because the reason is the size of the groups that are attached to the carbon, right? So here, this could be a long chain, by the way, right?
Yeah.
This could be a big group of carbon atoms, right? And this could also be a big group of carbon atoms, right?
Yeah.
Here, there is one big group, but there is only hydrogen here, right?
Yeah.
So think about it. When you actually did the reaction from ketone to this, you are going from sp2 to sp3, right?
sp3, yeah.
Yeah, yeah.
Right? So actually bond angles are decreasing near the carbon. Central bond angles are decreasing from 120 to 109 degree, right?
Yeah.
So if this decrease is happening, then if it is already very crowded, it will be difficult to decrease, no?
Yeah, yeah.
Like near the carbon, if there are big atom groups, right? This decrease will be not favored, no?
Yeah, yeah.
Right? Here, this size is very small, okay? So it doesn't crowd too much. So it is more favorable to decrease the bond angle here as compared to decreasing the bond angle here.
Yeah.
Yeah.
So therefore, the equilibrium is more favorable for this, right?
Yeah.
So you get better yields for aldehyde cyanohydrin formation, right?
Yeah.
Yeah.
Correct. So this reduction in bond angle is not a problem for aldehydes because one of the substituents is just a very small hydrogen atom. But for ketones, especially one that carry large alkyl groups, right? This effect can disfavor the addition reaction, right?
Yeah.
Yeah.
Effects that result from the so one important point here, effects that result from the size of the substituents, right, and the repulsion between them are called steric effects. So so now this particular difference in equilibrium position was only due because of the size of the groups, right?
Yeah.
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 Size of the groups and the hindrance that happens as a result of their size, right? So that is called steric effect, and this effect is called steric hindrance. It's a consequence of the repulsion between the electrons in all the filled orbitals of the alkyl substituents. So obviously, like here there are carbon, right? There are many carbons here, and each
Yeah.
carbon will have its own filled set of orbitals, right?
Yeah.
If you bring so many carbons close to each other, there will be repulsion basically. That repulsion force is what is preventing it to easily become this sp3 state, right?
Yeah.
Yeah.
Okay. Steric hindrance, so he's talking about that. The size of substituents plays a role in very many organic reactions. It's the reason aldehydes are more reactive than ketones, for example. Steric hindrance affects reaction rates, but also makes molecules react by completely different mechanisms, as you will see in the substitution reactions in chapter 15. So for example, he's saying he will show in chapter 15 that sometimes steric hindrance plays such a major role that the reaction doesn't even go as you would expect it to go. And a completely different thing will happen because it is so big and bulky that it cannot react by the expected pathway. Okay. So you will find that there will be a major difference if the groups are big. There will be a major difference in how one molecule reacts and how another molecule reacts, right?
Yeah.
Yeah.
Which is another point which reinforces our idea that structure will influence reactivity, right? So here clearly the structure and the size of the groups attached is going to influence how something reacts.
Yeah.
Yeah. Yeah.
So that will come more again and again. You will see that. Okay. Now this box, the next box is quite interesting. It's about cassava. Cassava is a staple fruit in Africa. It's like potatoes here. They eat cassava. Okay. And a lot of the times bodily enzymes, right, can act on the cassava. And so for example, look at this complicated thing that is there, right? That is that is a glucoside of acetone cyanohydrin found in cassava. Okay, that is a compound that comes in that vegetable, right? Now a bodily enzyme is acting on this, and it becomes this O something becomes OHCN. Okay,
Yeah.
it breaks that part apart. The red part goes away. Okay,
Yeah.
and it becomes OHCN, and another enzyme can make it a ketone and release CN minus. So these two enzymes are there in our body which can convert this cyanohydrin and release cyanide, right? CN minus, right?
Yeah. Yeah.
So what happens is, see, what is he saying? A meal of the glucoside is not poisonous in itself. Basically, the initial stuff was not poisonous, but enzymes in the human gut break it down and release HCN. Eventually, 50 milligram of HCN per 100 gram of cassava can be released, and this is enough to kill someone. Okay, so after a meal of unfermented cassava, so you have to ferment it and all before you can eat it. So if cassava is crushed with water and allowed to stand, enzymes in the cassava will do the same job, and then the HCN can be washed out before it is cooked and eaten. So basically, first you ferment it and then you remove the HCN already, and then you eat it. So this is quite interesting. Also, see this. Some diseases found in eastern Nigeria can be traced to long-term consumption of HCN, right? Similar,
Yeah.
glucosides are also found in apple pips, apple seeds, and the kernels inside the stones of fruits such as peaches and apricots. Some people like eating these, but it is unwise to eat too many at one sitting. So this is interesting. So because sometimes people say, no, those apple seeds are not good for you and all, right?
Yeah.
Mm-hmm.
So we cannot eat too much because
Yeah.
cyanide can be formed in your body. Anyway, angle of nucleophilic attack on aldehydes and ketones, right? Angle of attack. So apparently there is a particular angle with which a nucleophile will approach a carbon double bond, a carbonyl group. Okay. So this is probably some advanced stuff which you don't really need for JE, but we'll anyway go through it. So what he's saying is the C double bond O, right?
Yeah.
Yeah.
This is a planar structure, right? This is a
Mm.
planar structure,
Yeah.
correct?
Yeah.
And normally you would have expected the pi bond to have formed like this, right? The sigma bond like this
Yeah.
and the pi bond like this, right? Above the
Yeah.
plane, right?
Yeah.
So normally you would have expected the nucleophile with its electron rich thing, right?
Yeah.
Nucleophile which is having a filled pair of electrons, right?
Mm.
Will come directly and come like this and form a bond with the carbon directly, and this has to break then, right?
Yeah. Yeah.
Something like this has to happen, right?
Yeah.
So if you go to the first page, the next page, you see maximum overlap with the pi star. So there is a pi star anti-bonding orbital on carbon, the brown one, right?
Yeah.
The brown one is the pi star, okay? So you would have expected that pi star was empty and the nucleophile will come with its green orbital and bond like this, right?
Yeah.
But actually the nucleophile doesn't come like that. It comes at an angle, okay? And what is the angle at which it comes? It comes at some 107-degree angle, this angle. It doesn't come at like this, okay?
Yeah.
So that angle is called the Borohydride's trajectory, the way it approaches. Oh, okay. And might not be super important for you, but why does it happen? The reason it happens is because there is a repulsion from the filled p or pi orbital. There is a repulsion. It doesn't want to come like this. There is repulsion from the filled p orbital, which forces it to attack like this. Okay.
Yeah.
Also, he also explains it in a way that actually the pi star orbitals, right? Not the pi
Yeah.
star orbital. The pi star orbitals are going to be at a tilted angle, no, because there is a node between the C and the O, right?
Yeah. Yeah.
So there is a node between C and O, so it's actually somewhat like this, the pi star orbitals. So when you draw pi and pi star, no, it is not vertical actually. So pi star is actually like this, and pi orbitals are actually like this. The bonding orbitals are actually like this.
Yeah. Yeah.
Because there is electron density between them when it is a bonding orbital, right?
Yeah. Yeah.
And there is a node when it is anti-bonding, right? So
Yeah,
it is
yeah.
actually away from each other, right?
Yeah.
So already pi star is at an angle, and that is why it is approaching at that angle. Okay.
Yeah.
Not super important. It's just there. Let's move on. We'll move on to the fact there is nucleophilic attack by hydride ion. Nucleophilic attack. This is quite interesting. Attack by hydride ion. So this hydride, what is this hydride stuff? It is H minus, right?
Yeah.
Okay, on aldehydes and ketones. So he talks about the fact that actually H minus cannot attack as a nucleophile. So he's saying nucleophilic attack by the hydride ion is an almost unknown reaction. Then why is he making the section name like that, right? You understand? The section name is saying nucleophilic attack by hydride, but there is a quotation marks on top, right?
Yeah.
Yeah.
So He's saying first line is it is an unknown reaction. The species, this species which is present in the salt sodium hydride has a high charge density. Obviously, this will be 1s2, just that's it, right?
Yeah.
Hydride ion.
One is-
So it is very small and it has one negative charge, right? So it
Yeah.
has a lot of charge density, right? So this filled 1s orbital is of an ideal size to interact with the hydrogen atom's contribution to the sigma star orbital of an HX bond. So what is he saying? The filled orbital 1s orbital is quite small, no?
Yeah.
Filled orbital is quite small.
Small, yeah.
So it will react. So if there is an H bonded to any atom like this, right, in a sigma bond, right?
Yeah.
So this is a 1s sigma bond, right?
Yeah.
Right? Because H will only form a 1s sigma types, right?
Yeah.
So the size of this filled orbital is of the perfect size to interact with this one. The sigma star here. Sigma star for this 1s bond, right?
Yeah.
So sigma star for this bond will be empty right now, no? Because there is a single bond. So sigma star will be empty, and this is a filled 1s sigma bond, a 1s
Sigma.
orbital, right?
Yeah.
So this is highest occupied molecular orbital for it, and this is lowest unoccupied molecular orbital here, right?
Yeah.
So the H minus has a tendency to attack these type of bonds, right? So what will happen is that H minus will attack this, form a bond with H, H2 will be released, and plus X minus, right?
Yeah.
Because this bond has to break then, right?
Break,
Correct. So this is a more typical reaction that happens, correct, with hydride ion. Okay. Now, hydride ion is too small to interact with the pi star orbital. Pi star orbital of carbon is of the 2p kind, right?
Yeah.
It is too big and diffuse to interact with the 1s2 orbital.
Okay.
There is a huge gap in energy, right?
Yeah.
So then the bonding gain will not be sufficient, right? Correct. So what he is saying is, look at the figure where there's a cross in the nucleophilic attack. Okay. So this never happens. H minus comes and hits the carbon and forms H carbon bond and O minus, right? That thing doesn't happen. What happens is H minus attacks any atom and breaks the sigma bond.
Yeah.
So here it would have broken the pi bond, right? Of the carbon. And here it is going to break the sigma bond of any hydrogen, right?
Yeah.
So H minus is coming and taking away hydrogen from something. That means H minus is acting like a base, right? H minus is acting like a base because the other one is acting like an acid, right? Giving H plus.
H plus. Yeah.
Right? And H minus accepts a proton. That is a base, right?
Yeah.
So H minus almost always reacts as a base, and it doesn't react as a nucleophile. Okay. So this is a clear difference. We said earlier that bases and nucleophiles are similar, right?
Yeah.
But there is still a slight difference, right? This is the difference. Like a base would accept proton, right? But nucleophile would have donated its electron pair, right? And it doesn't matter whether it accepts a proton or not, right? Like a base is a very specific action. It is taking a proton right here.
Yeah.
So H minus will almost always react as a base, but it doesn't react as a nucleophile, right? Nevertheless, addition of H minus to the carbon atom of CO group would be a very useful reaction. Because why would it be useful? Because the result would be the formation of an alcohol. Why? Because this O minus would have been formed, right? And then it could have been hydrated and it will become OH, right?
Yeah.
And that would be an alcohol, and alcohols are useful in industry for many processes. So that would be a nice reaction if you could somehow manage that, right? So the way it can be done is not by direct addition of H minus, but by compounds like sodium borohydride. So BH4 minus. Okay.
Hmm.
So there is a tetrahedral BH4 minus anion, right? Correct.
Yeah.
Yeah, yeah.
Now we have already seen BH4 minus earlier. We saw BH3 was electron deficient.
Yeah.
Right?
Yeah.
BH3 would have been electron deficient. There are 6 electrons, and that's all that boron has, right?
Boron mass.
Hmm.
Yeah.
So, but BH4 minus on the other hand, right, is filling the octet of boron, right? And there is
Yeah.
a negative charge, right? Remember
Uh-huh.
that there is no negative charge because of any lone pair here. The negative charge is because H minus was added to this, and boron didn't have more than 6. Okay.
Yeah.
Yeah.
So there is no vacant lone pair somewhere.
Vacant. Yeah.
Okay. Then the electrons that will come out from this will come out from some bond being broken.
Yeah.
Okay.
Hmm.
So this BH4 minus, since it is a negatively charged thing, it is obviously going to be nucleophilic, right?
Yeah.
Yeah.
It is obviously going to be nucleophilic.
Nucleophilic.
So
Yeah.
this BH4 minus is obviously going to be able to attack the ketone or aldehyde, right?
Yeah. Yeah.
BH4 minus has the potential because it's nucleophilic, right? And
Yeah.
this is tiny positive, right? Correct. So
Hmm.
when it attacks, what will happen here? There is no lone pair to come. Okay. The
Yeah.
bond itself must break.
Yeah. Yeah.
The bond itself must break, and it will take the H along with it, right? Because bond
Yeah.
breaks means H becomes free, right?
Yeah.
And the 2 electrons with it come here and bind with this, right?
Yeah.
So
Yeah.
technically you're still adding a H minus, right?
Yeah. Yeah.
And you're getting an O minus, right?
Hmm.
Because this comes here, right?
Yeah.
You understand?
Yeah.
And what is happening to BH4 minus? It becomes BH3,
BH3.
BH3.
right?
Hmm.
And so it looks like you have added H minus, but actually you cannot add H minus directly. Okay.
Yeah.
You understand? So that is why there was quotation mark there, right?
Yeah.
It is
Yeah.
still addition of hydride ion somehow, right? But through another thing. So through NaBH4, right?
Yeah.
And it is nucleophilic addition only because this lone pair of this pair of electrons which is in a bonding sigma bond breaks, and it
Breaks.
comes with the H minus and attaches here, and this becomes this, and then you protonate it and you get the alcohol.
Yeah. Yeah.
Then it becomes OH, right?
Yeah.
So that is what is happening. So what happens when we carry out this reaction using a carbonyl compound as the electrophile? The hydrogen atom together with the pair of electrons from the borohydride BH bond, right? From the BH bond will be transferred to the carbon atom of the CO group, right? Although no hydride ion H minus is actually involved in the reaction, the transfer of a hydrogen atom with an attached pair of electrons can be regarded as a hydride transfer, right?
Yeah. Yeah.
You will often see it described this way in books, but be careful not to confuse BH4 minus with the hydride ion itself, right?
Yeah. Yeah.
To make it quite clear that it is the hydrogen atom that is forming the new bond to C, this reaction may be helpfully represented with a curly arrow passing through the hydrogen atom, right? So this arrow can pass through the hydrogen atom so that you know that this hydrogen atom also goes and attaches, right?
Yeah.
Yeah.
And eventually you are getting what you want to get, right? So
Yeah.
BH3 comes out. Okay, so fine, you met this reaction in chapter 5, but there is more to say about it. Okay, so what more is there? The oxo anion formed, right? The oxy anion produced in the first step. So for example, first step we get this, right? This is the
Yeah.
oxy anion, right?
Yeah.
Can help stabilize the electron deficient BH3 molecule by adding to its empty p orbital.
Yeah.
So here the BH3 was empty p orbital, no, nothing was there.
Yeah.
So the oxo anion can give its 2 electrons to it, right, and form a bond, right?
Bond. Yeah.
So it will become something like this: CCHO B, right, and H3, right?
Yeah.
Something like this it can become, right?
Yeah.
Correct. And the overall thing will now have negative charge.
Yeah.
Yeah, yeah.
Correct. Because charge cannot be destroyed, right?
Yeah.
Correct. So overall thing will have negative charge, and there a complex type of compound has been formed, right? The reason this is better than that, this is better than this situation, is because uh, right now BH3's octet needs have been satisfied here, right?
Yeah, yeah.
And charge is also distributed over the bigger molecule, right?
Yeah.
Charge is not just over a oxygen here, it is distributed over this whole region now, right?
Hmm.
Correct.
Yeah.
So
Yeah.
now we have a tetravalent boron anion again, right? So so you have a tetravalent boron. So again now you have a tetravalent boron anion, right? Which could again give its H plus, right?
Yeah,
Yeah.
yeah.
To another molecule of aldehyde, right?
Hmm.
So basically, again there is a tetravalent stuff. No, again this can break, right?
Yeah,
Yeah.
yeah.
Again, this
Like
one.
BH4 minus, like instead of BH4, now suddenly it has become BH3 and something else, right?
Yeah, yeah.
And again it can break, again it can go to another aldehyde, again form an oxoion, again oxoion can stabilize it, right?
Hmm.
Like things like this can happen. Okay, the process can continue, so that in principle all four hydrogen atoms could be transferred to molecules of aldehydes, right? So
Yeah.
notice
Yeah.
from this step to this step, out of the four hydrogen atoms one has gone, right?
One.
And in principle you can remove all four like this.
Yeah.
Okay.
Hmm.
However, the reaction is rarely as efficient as that. It will not be you will not be able to get good enough yields. Like after a point, you know what will happen? Steric hindrance, right?
Yeah, yeah.
Like this will not add back to BH3 if there are already one or two attached, right? It will not be able to attack it only, right?
Yeah. Yeah.
Because there is too bulky, right?
Too bulky.
There will be steric hindrance, it will not work, okay, after a point. So
Yeah.
overall the reaction you have understood, no, what is happening.
Yeah. Yeah.
Yeah, yeah.
BH4 minus is giving H minus to the carbonyl group, right? And H minus is coming there forming a bond, then oxoanion is formed, you can hydrate it and it will become alcohol, right?
Yeah.
Yeah.
So the first step, so if you look at the examples of reductions with sodium borohydride, why is it called a reduction? Because hydrogen is being added, right? So when you learned basic chemistry, you knew that reduction was addition of hydrogen, right?
Yeah.
Yeah,
Or
yeah.
removal of oxygen, right?
Removal of oxygen.
So here what is happening to the MEOCHO? There's an aldehyde here, right?
Yeah.
This aldehyde, the first step is NaBH4, and because of NaBH4, the H minus comes on that carbon and O minus it becomes, right?
Yeah, yeah.
The second step is add water to it, and what it will protonate it.
Yeah. So OH,
So
yeah.
OH it will become, right? So eventually you are forming a carbon OH and HH, right?
Yeah, yeah.
Right. So H has been added, so it's called a reduction, right?
Okay,
Similar
yeah.
things are happening in other two examples also. Okay. So
Yeah.
these are reductions by sodium borohydride, right?
Yeah.
So he's saying sodium borohydride is one of the weaker hydride donors. The fact that it can be used in water is evidence of this. So for example, more powerful hydride donors like lithium aluminum hydride, LiAlH4, okay, that will be more powerful than sodium borohydride, okay.
Yeah.
It reacts violently with water itself. With water itself it will react, so you cannot do that reaction in water, right?
Okay.
Sodium borohydride reacts with both aldehydes and ketones, although the reaction with ketones is slower for the same reason that we knew earlier, right?
Yeah, steric hindrance.
Yeah.
For example, benzaldehyde is reduced about 400 times faster than acetophenone, right? This is because of steric hindrance.
Yeah.
Okay. So sodium borohydride does not react at all with less reactive carbonyl compounds such as esters or amides. Less reactive carbonyl compounds. So there are other compounds also that have carbonyl group, right? So for example, if you have CO, RCONH2, right?
Yeah.
That is an ester, that is an amide. Okay.
Hmm.
And if you have RC double bond OR, that is an ester. Okay. So these are less reactive than aldehydes or ketones, and sodium borohydride does not react with them. Okay. So if a molecule contains both an aldehyde and an ester, right, only the aldehyde part will be reduced.
Yeah, yeah.
Okay. So look at that molecule that is there, the with the ring, right? There is a CHO on one end and there is a COOET on one end, right?
Yeah.
ET stands for ethyl, C2H5. Okay. So the ET part, right? ET means ethyl, ME means methyl. You know this, right?
Yeah. Yeah.
This was discussed in the second chapter of this book, right?
Yeah.
He had named some of these things. You should know the names and structures, right?
Yeah.
So he will not be writing that all the time. So here, for example, this particular compound is basically C double bond O, and there is a C2H5 here.
Yeah.
And this is a single bond. So this is clearly
The
an
ester
ester,
part.
right? And this part is the C double bond O. This is the aldehyde part.
Yeah.
So if you add NaBH4 in some solution, ETOH. ETOH is basically C2H5OH, alcohol.
Yeah.
Okay. So
Yeah,
this is a solvent. So you are adding it instead of water, you're using ETOH, right?
Yeah.
And so first it will reduce it and it will just affect the
Aldehyde.
aldehyde part, and it will become OH
OH.
and H and H, right?
Yeah.
And this side it is still C double bond OET, right?
Yeah.
So that is what is happening there. Okay. The next two examples illustrate the reduction of aldehydes and ketones in the presence of other reactive functional groups. See, no reaction occurs at the nitro group in the first case, NO2 group, right?
Yeah.
And in the second case, the Br is also unaffected. Only so other groups like nitro group or alkyl halide, here there is a Br group, right?
Yeah.
It's called an alkyl halide. Okay. Because the halogen is being attached to a carbon.
Yeah.
So some alkyl group has a halogen, so it's called alkyl halide. Okay. So that group doesn't have any effect, right?
Yeah.
Okay. Then we come to addition of organometallic reagents to aldehydes and ketones. Organometallic reagents to aldehydes and ketones. So what is this organometallic compounds? These are compounds that have a carbon and metal bond, right? So this is very important. Organometallic compounds will have a carbon metal bond, right? Now understand that the carbon metal bond will be such that carbon will be electronegative, right? This will be highly electropositive, right?
Yeah.
Right. So this carbon is electron rich, right?
Yeah.
And this bond is very breakable. This bond is completely breakable here, right? Because it is a polarized bond, highly polarized bond. So if you have, say, RMgX or something, X can be anything, or you have RLIX, right?
Yeah.
So this carbon here will be completely, this bond can be broken, right?
Yeah.
LIC or MgC bonds are highly polarized towards carbon. They are therefore very powerful nucleophiles. So if the carbon has a negative charge, it will be nucleophilic.
Yeah.
They will be very powerful nucleophiles. So what can they do? They can attack the carbonyl group, right?
Yeah.
To give alcohols forming a new CC bond. So what is happening here? So for our first example, we should take one of the simplest of organolithiums. So methyl lithium, right? So what is it? CH3Li, right? CH3Li, which is available as a solution in ET2O, shown here, reacting with an aldehyde. Okay, fine. So you are reacting MELI or methyl lithium, right?
Yeah.
With the aldehyde, right? So look at the below, look at below, it is LIME, that bond is going to break, right?
Yeah.
And carbon will come with that lone pair. So see, Li plus is possible, right?
Yeah.
Li plus is totally stable. It can exist like that, right?
Yeah.
So Li plus it will become, and Me will come with the 2 electrons and add to the carbon. So it will form a bond with the carbon-carbon bond, and O minus will happen, and then there is a second step where you add water, right?
Yeah.
And you will get the OH again. Right?
Yeah.
Correct. So polarization of the metal and carbon bond is resulting in carbon being the electrophile here, right?
Yeah.
This carbon atom is the electrophile, and it can attack the CO bond and form basically an alcohol, right? By
Yeah.
nucleophilic addition.
Mm-hmm.
The course of the reaction is much the same as you have seen before, but we need to highlight a few points where this reaction scheme differs from those you have met earlier, right? First of all, note that it is written 1 MELI-THF and 2 H2O. Okay.
Yeah.
What does that mean? There is a first step where you add the organolithium compound, and you are adding a THF. THF stands for tetrahydrofuran. It's a solvent. Okay. It's a non-polar solvent. It's like water. It doesn't do anything. It's just dissolving the CH3Li. Okay. So it is unreactive, and you are using that as first step, and second step is water. You cannot add water in the together. You cannot do it.
Okay.
Because then CH3Li will react with water then.
Yeah.
Okay. So this means that first MELI is added to aldehyde in a THF solvent. Reaction occurs. MELI adds to aldehyde to give an alkoxide. Then and only then water is added to protonate the alkoxide. Okay. So water has to be added in a separate step. It is not present at the start of the reaction as it was in the cyanide reaction and some of the borohydride addition reactions, right? In fact, water must not be present during the addition of MELI or of any organometallic reagent to a carbonyl group, because water destroys organometallics very rapidly by protonating them to give alkanes. So for example, what will happen is LiMe will react to form LiOH and MEH. CH3 minus will come. No, CH3 minus will just take a hydrogen from water. That will become methane. Which is much more stable. And LiOH will be formed, right? So the organometallic will be destroyed if you add it with water. Okay. So because they are so reactive, organometallics are usually stored at low temperatures, often -78 and so on, right? Protic solvents such as and they are kept with aprotic solvents. Aprotic solvents means they don't have a transferable H plus, right? So ET2O, tetrahydrofuran, these are solvents which don't have hydrogen that can be given as an acid. H plus it cannot get released. Water and alcohol, on the other hand, can release H plus. So you cannot store it in that. Okay. Normally, most of the compounds you can store it as dissolved in water or alcohol solution. So you have to be especially careful here, right? Now, okay. Then the next important thing is, note that addition to an aldehyde gives a secondary alcohol, while addition to a ketone gives a tertiary alcohol. So what does he mean here? So suppose you have R C double bond O H, right? And you added CH3Li, right? So you end up getting RCCH3 OH H, right? This alcohol, right? So now this alcohol comes. Now this is the alcohol group OH. Okay. So this is attached to the carbon, which is itself attached to 2 carbons, right? So when the carbon connecting the OH group is attached to 2 other carbons, right? That is called a 2-degree alcohol, secondary alcohol. Okay. But if you took a ketone and started with a ketone, right?
You get tertiary.
Then you should get a tertiary alcohol, right? Because Finally, it will become RCCH3 ROH, right?
OH,
Yeah.
yeah.
So
So
this
3 carbon.
particular alcohol is connected to 3 carbons, right?
Yeah,
Yeah.
yeah.
That is a 3-degree alcohol.
Hmm.
So if you want to, the question will be in this way that you have to synthesize a 2-degree alcohol, right?
Hmm.
Or you have to create a 3-degree alcohol somehow, right?
Hmm.
So
Yeah.
you
Yeah.
should choose a ketone with an organolithium, or you should choose an aldehyde with a organometallic compound, right?
Yeah,
Yeah.
yeah.
And reduce an aldehyde or a ketone to be able to get the correct 2-degree or
2
3-degree
degree.
alcohol, right?
Yeah. Yeah.
Mm-hmm.
So that is why he is mentioning it. Okay. Then he is talking about organomagnesium reagents. Organomagnesium reagents called known as Grignard reagents. These are very famous. This is very important. Organomagnesium compounds like Grignard reagents, which react in a simple way. So here X stands for a halogen. Okay.
Hmm.
X is a halogen. Now, and this is Mg and this is R, right?
Yeah.
So they react in a simple way because again CH3, the bond here is quite polarized, right? Correct.
Yeah.
The
Mm-hmm.
Yeah.
bond here is quite polarized. The reaction happens in the exact same way, right? Uh,
Hmm.
so look at the reaction RCHO plus pH MgBr, right? So pH will
Hmm.
attach, right? pH will
Yeah.
attach and it becomes O minus and then it becomes OH in the second step,
Yeah.
right?
Mm-hmm. Yeah, yeah.
So there is no difference in the action of this on aldehydes or ketones,
Oh.
or R, C, R, right? The
Hmm.
same
Hmm.
action happens, it becomes alcohols,
Yeah.
right?
Yeah,
Yeah.
yeah.
How do you get these Grignard reagents? So on the side box, he is talking about these are made by reacting alkyl or aryl halides with magnesium. So PHBr. So you take PHBr, which is phenyl group,
Hmm.
and add magnesium, you will get PHMgBr. So basically, this one is like this.
Hmm. Hmm.
So generally, each one has two. Okay,
Mm.
two or one. Uh,
2.
C6 at 6. It should have been one. Oh, why am I doing two? It will be one. No?
Hmm.
We are the double bonds. Yeah, yeah.
So it is like this. Generally,
Yeah.
the group is like this,
Yeah,
and
yeah.
each
So,
one has one hydrogen. Okay,
yeah.
Yeah.
this is your benzene. Okay,
Hmm.
this is your benzene C6 at 6.
Yeah. And
Okay,
then,
and if one of them is Br, that is your PHBr.
yeah.
Yeah, yeah.
Okay, and plus Mg will become
MgO.
PHMgBr.
Yeah.
Okay, so anyway, that doesn't matter. The idea is that again organometallics will also behave like typical organo Grignard reagents will behave like typical organometallics, right?
Mm-hmm. Yeah.
Addition of water to aldehydes and ketones. Okay, so
Hmm.
nucleophiles, he's saying nucleophiles don't have to be highly polarized or negatively charged to react with aldehydes and ketones. Even neutral nucleophiles will do that reaction. Okay, so go to the
Hmm.
next page. So what is happening is water is acting with formaldehyde. Okay, ignore the spectroscopic parts. So water will act on formaldehyde. So formaldehyde structure will be HC double bond OH, right?
Mm-hmm.
And water. So water has to act as a nucleophile here. So
Hmm.
so the electron pair on the oxygen will be one that will form a bond, right?
Yeah. Yeah.
Right. So you will end up getting uh, there will be a H2O that will add here. So what will happen
Plus
is
P plus H plus.
C double bond O, H, H and O, right?
Hmm.
H, H double bond, right? And there's a tiny positive that comes here, right?
Yeah.
Because O has lost 2 electrons and got back only one, right?
Yeah. Yeah.
Mm-hmm.
And this bond must break and it becomes a
Great.
tiny negative, right?
Yeah.
Correct. Now, what will happen is this tiny positive will go, the H plus should break here, no? H plus
Yeah.
should break here. H plus will come out, and the two electrons will come here, and it will be a typical O here, OH here.
OH. Yeah.
And
Yeah.
later this H plus will hydrate this.
Yeah.
Okay. Okay. Yeah.
You understand? You'll get a
True.
diol.
Mm-hmm.
You understand?
Yeah.
Yeah.
So it is not very clear in my diagram, but I'll draw again. So you have a double bond O, right? H,
Mm.
H. And you
Yeah.
have water, which is like this.
Mm.
Okay. And one of them will come here, form a bond.
Yeah.
So intermediate step will be HOH. There is one here. There is a tiny positive because bond has been formed, right?
Yeah.
Yeah.
And there is a O minus here because
Yeah.
this bond has to break them.
Mm-hmm.
And this is the situation, right?
Yeah.
Yeah.
Now, it is highly likely that this is not stable. Oxygen cannot have
Yeah,
positive
cannot be
charge.
stable.
Okay. So
Mm-hmm.
these two electrons will come here, right?
Yeah.
Mm.
And stabilize the oxygen. And that results in breaking of this bond, right?
Yeah.
But both the electrons will come here. So it will come H plus and come out, right?
Yes.
Yeah.
Yeah.
So it becomes O double bond, two lone pairs, H, C, O minus, H, H plus H plus, right?
Mm.
Yeah.
And the H plus proton will attack this,
Oh my. Yeah. Yeah.
right? And it will become OH here, C, and this will become also OH and H, right?
Yeah.
Mm.
So you end up getting a diol or double alcohol, right?
Mm. Yeah.
Correct. So
Hmm.
formaldehyde, this reaction. So let's look at what he is talking about here. Formaldehyde is an extremely reactive aldehyde as it has no substituents to hinder attack.
Mm.
It
Yeah.
is so reactive that it is rather prone to polymerization, and it is quite happy to move from sp2 to sp3 hybridization, right?
Mm.
Because there is very little increased steric hindrance between the two hydrogen atoms, right?
Yeah. Yeah.
This
Hmm.
is understandable. Fine. A mechanism for the hydration reaction is shown below. Notice how a proton has to be transferred from one oxygen to the other, mediated by water molecules.
Mm.
So proton from the H2O has gone to the O there, right?
Yeah.
Yeah.
And the process is the same almost.
Yeah. Yeah.
H2O added, H2O plus, then O minus, and then, okay, then what happened? The next step was H. Okay, so outside, so it doesn't have to be like automatically on its own it lost an H. It could be because H2O from here took an H and it became H3O plus
Mm-hmm.
in the solution. Okay,
Yeah. Yeah.
and that H3O plus in the solution acted on this.
Yeah.
Okay. Yeah.
Right.
Yeah.
It doesn't have to be the same hydrogen atom doing all the work, right?
Yeah.
Mm.
There are so many water molecules around it, right?
Yeah.
The
Mm-hmm.
water molecules are doing the mediation. They are picking up the hydrogen from here, and then they are giving other water molecules are giving a hydrogen here,
Yeah. Yeah.
right?
Yeah.
You understand?
Yeah.
It doesn't have
Mm-hmm.
to be the same atom that comes out from here and goes there, right?
Mm-hmm. Yeah. Doesn't.
It is more likely that water molecules will do that picking up and dropping it off,
Yeah. Yeah.
right? Okay.
Yeah.
So formaldehyde reacts with water so readily because its substituents are very small. A steric effect, right? Electronic effects can also favor reactions with nucleophiles. So electronegative atoms such as halogens attach to the carbon atoms next to the carbonyl group, right? So
Mm.
Yeah.
if you have electronegative atoms like halogens next to that carbon atom of the carbonyl group, right?
Mm.
It will increase the extent of hydration. It will increase the formation of that alcohol and all because of inductive effect.
Yeah.
So this is the inductive effect first time he is mentioning here. Okay. So what
Mm-hmm.
is happening is the halogens next to the carbon atom will draw the electrons away, right?
Yeah.
Yeah.
Correct.
Yeah.
So
Yeah.
it will become even more, the carbon will become even more positive,
Positive. Yeah.
Positive.
right? So it
Mm.
is more powerfully going attracting nucleophiles then, right?
Nucleophile, yeah.
Yeah,
Correct.
yeah.
So they increase the polarization of the carbonyl group, which already has a positively polarized carbonyl carbon,
Yeah.
and therefore makes it more prone to attack by water,
Mm.
right?
Mm-hmm.
Yeah.
So trichloroacetaldehyde, CCl3CHO, right,
Yeah.
Mm-hmm.
has so many chlorines which are pulling away the electron density, right?
Yeah. Yeah.
Yeah.
So the carbon on the double bond, that carbon is
Yeah.
going to be very positive
Very
here,
positive.
right? So it will be hydrated completely with water, and the
Mm.
product chloral chloral hydrate can be isolated as crystals. Okay.
Mm. Yeah.
So this hydration reaction we have just now seen, basically H2O is being added to an aldehyde or a ketone.
Yeah.
Yeah, yeah.
Uh, he is also on the next page. He is also showing chart shows the extent of hydration for a small selection of carbonyl compounds, right?
Mm.
So look at acetone. The equilibrium constant he has mentioned for each of them, right?
Yeah. Yeah.
The acetone equilibrium constant is quite low.
Mm.
Acetaldehyde is much higher than that, 1,000 times higher.
Yeah.
Mm-hmm.
Formaldehyde is even higher, right?
Mm.
Yeah.
Chloral hydrate is also quite high, right?
Yeah.
And hexafluoroacetone is very high. See,
Yeah, yeah.
Process.
the formation of this, the equilibrium constants for the top reaction he's talking about, right?
Mm. Mm.
For each of the different compounds, the K value is different, right?
Yeah.
Okay. Then he says cyclopropanones or three-membered ring ketones. So, for example, that cyclopropane is this triangular ring. Okay.
Mm.
Mm-hmm.
So for example, this is cyclopropane, right? So each of them have two hydrogens,
Yeah.
right?
Mm-hmm.
So this compound will be C3H6, right?
That's it.
This is cyclopropane. Now he's talking about right now cyclopropanone, right? So there is a
Yeah.
ketone group here,
Mm.
and this will be hydrogen, hydrogen, and all, right?
Mm. Yeah.
So cyclopropanone is also hydrated to a significant degree. Like the K value for hydration of this, right, will also
Mm.
be high.
Aye.
Basically, it will also give you the OH
Yeah.
Yeah, yeah.
OH to a substantially high degree. And the reason, however, is slightly different. So he's saying you saw earlier how acyclic ketones suffer increased steric hindrance when the bond angle changes from 120 to 109, right?
Yeah.
Yeah, yeah.
Mm.
Correct. Cyclopropanones and other small ring ketones. Small ring ketones means they are tiny rings, maybe
Yeah.
butanone also, right?
Mm. Mm.
Mm.
Butanone also will behave in a similar way, right?
Yeah.
When they are a small ring, they prefer they conversely prefer the small bond angle because their substituents are already confined within a ring. Look at it this
Mm.
way. So he's saying a three-membered ring is really very strained with bond angles forced to be 60-degree, right?
Yeah,
Yeah.
yeah.
Mm.
For the sp2 hybridized ketone, this means bending the bond 60-degree away from their natural 120-degree, right?
120.
So naturally, sp2 hybridized ketone should have been at 120, but because of this cyclic group, it is forced to be at 60, right?
Yeah.
Mm-hmm.
So it's already very strained, right?
Yeah.
So if you are happening to go to a state where your sp3, you are going to have a ideal angle of 109, right?
Mm.
Yeah.
So because of this ketone, the strain is going to be less, right?
Reduced. Yeah.
60-degree to 109 is not as big strain as compared to this, right?
Yeah. Yeah.
The ideal angle is 120 and you are at 60, right?
60.
Mm.
So actually it favors this because of steric effects, right?
Yeah.
Mm-hmm.
There is less steric strain if it forms the sp3 compound, right?
Yeah. Yeah.
Correct. So some
Yeah.
of the strain, so addition to the CO group allows some of the strain inherent in the small ring to be released,
Reduced. Yeah.
right? So
Mm.
hydration is favored, and indeed cyclopropanone and cyclobutanone are very reactive electrophiles.
Mm-hmm.
So they will be very eager to go through this reaction, right?
Yeah, yeah.
Okay. Then we have a couple of sections left. Okay. The one section is hemiacetals, aldehydes and ketones. Reaction of alcohols will form hemiacetals, and then there is acid and base catalysis. Acid and base catalysis of hemiacetal and hyd. Basically, two reactions: the hemiacetal stuff and then bisulfite addition. Right.
Mm-hmm.
That is the end of the chapter. So I would like you guys to read through this. Okay, these two reactions. There are 4 pages. Okay.
Yeah.
Read through this. Also, the homework for this will be now low. I have shared another book, right? The problem book, right?
Yeah, yeah.
So problem book for this Clayden, right? So I want you guys to go through chapter 5 and chapter 6 problems.
Yeah.
The previous chapter, which is also reactions and all, and it had electrophiles and nucleophiles, right?
Yeah.
Go through the problem book, chapter 5 and chapter 6. So next class will not be new theory. Next class will be if there is any doubts in the last 2-3 pages, and we'll be doing the problems.
Okay.
Chapter 5 and chapter 6 of this book.
Yeah.
Okay.
Mm-hmm.
Once we are done with the problems of chapter 5, chapter 6, we'll go on to chapter 7.
Okay.
Okay. So delocalization and conjugation and all is very important. Now we are coming into the main chapters. Okay.
Yeah.
Already this chapter is super important. So nucleophilic addition and all you should understand, and it is fairly straightforward right now. Right?
Yeah.
Okay. So do the questions now. It will solidify everything that you have learned.
Yeah.
Do these questions. Next class we'll discuss this. Okay.
Okay.
Okay. That's all for now then.
Okay. That's it.
Bye.
Bye, sir.